It's Steve, and this is Brainless Raider, a puzzle adventure game made in 3 hours for Trijam 276. In this series, we're going step by step over the process of remaking the game in Bevy, the Rust game engine, in probably closer to 3 months. So last time on this series, we got our little dudes moving around and actually obeying the paths set forward for them. This time, we will do some basic collision detection, which the result of that will probably just be a whole bunch of console logs saying, hey, this thing collided with that thing, collided with this thing, whatever, or uncollided with those things, so on and so forth. In the original game, and this is how we're going to do it in this one too, basically all the collisions were circle colliders. So if you imagine like a tiny little circle inside of each of these, and then that's what we're actually testing on. That's a very efficient way to do collision detection. Not that this game requires efficient collision detection. It's pretty simple, but it's also really easy to implement. We don't need anything more complicated than that in this game. So that's how we're going to do it. Let's get into it. Let's just go through all of the templates that require collision, and we're just going to add a basic level of collision radius. So how we're going to do this is we're going to actually define a collider component, and this is going to be used on everything that has collision. And we're also going to need a float defining the collision radius. So I'm thinking that's 4 pixels. So these are all 16 wide, right? And a 4 pixel radius would be about half the radius total. Effectively a circle about that big inside of each of them. There's going to be some things with pits and planks and stuff later that we're going to need to change the size of that circle. So let's go through all of these real quick. Here we see a downside of this system. We need to make sure that these properties are all named the same, because we don't have any way of enforcing that through the way we're doing this. That's the downside of a simple to implement system. Usually it's not as easy to use. Turns out, as adding user experience is actually a complicated problem to solve. Hey, this one already has a collider. We have colliders on everything that needs them. So just checking in on the templates real quick, we now have a collider radius float with a value of 4. I like to use the standard of 1 feature per component. So since we're adding a new feature here, which is collider, we're going to add a new component for it. I don't know if we'll need constants or helpers, but might as well define them. I know we will need events and we will need components and systems. So let's get to defining that plugin. So here's our plugin. All right, let's start out by defining our collider itself. This is what we're going to be hydrating when we detect that collider component on that entity. So here's our struct. As you can see here, we're going to save the radius. We're also going to save its name so that we can use it in a debug message. And then colliding with, we need to keep track of this list because when things collide, they need to hold on to the reference of the things they're colliding with so that when they're no longer colliding, our collision detection isn't going to find things that aren't colliding that were once colliding. The only way we would know that if they're holding references to each other. And then we'll say, hey, you're not colliding, but you're holding references. That means you just uncollided. Let's clear that reference and shoot off that event. That's why we have this. We also need a couple of events that we want to shoot off, so let's do that. Shoot off, a very technical term when it comes to events. Firing our events, that's actually the term I'm going for. Luckily, Bevy has a little event abstraction built in. And simple as this, the two entities that are colliding with each other. There's really no order of precedence here, so we're going to have to develop that later. But for now, it'll just send out a couple of entities that were colliding with each other. It's not enough just to define the events like that. We also have to add them into our app, so let's do that. There we are. What else do we need? Oh, let's define a hydrator for this collider too while we're at it. There's a lot of pre-work to do before we actually get to the implementation here, but we do need to hydrate this, so let's do that real quick. Hopefully you can see why I like the hydrator pattern for this. It's almost like having a constructor, but a constructor that's always going to be based on the object data in our template, which is awesome. I like it personally. And here we are. We're pulling collider radius and setting that into radius. We are grabbing the object type from object data, which you can look back probably 10 episodes at this point to figure out what object data even is, but it's effectively a representation of what's in our template, including the type, which is where we're getting the name from, and of course all the properties. And then colliding with is just being initialized to an empty vector. We need to actually call this hydrator, so let's go back over into main real quick and find where we're registering our hydrators. Simple as this, register. See, now we can chain hydrator registrations and just build up a little list here, which is cool. Effectively, a very similar pattern to building the app, so it feels Bevy-ish to me. So let's make a system for keeping track of our colliders and updating them. So to start with, we are just going to pull in all of our colliders, which we need the entity reference, we need the transform to tell where the entities are, and of course we need the collider reference to use the radius and the name, and we also need to be able to mutate the colliding with list. There's a really cool function in Bevy that helps us out a lot with this. So this is iter combinations mute. What it does is it'll go through a one-dimensional vector and grab the combinations of every pair of objects. So if there's 3 objects, then it'll take these ones, and those ones, but it won't duplicate any of that, which is exactly what we need to do in this instance. So it's really handy that this exists. Hey there, Alucard. How are you? That's a great anime. I love it. So let's do our loop. Like pretty much every other Bevy system, we're just gonna loop. So here we're grabbing a combination. This is the combination we were talking about of the first entity and the second entity, which follow these rules. Mutable collider 1, mutable collider 2. So basically, we're going over every single one of those combinations here. Let dist. So let's pull our dist out here. Obviously, distance is just going to be the distance that we need to be for it to be considered touching or overlapping even, and we're just going to square that for dist 2. So here we have effectively just checking the distance and checking if they're overlapping. In the hopes of getting feedback as quickly as possible here so we know we're not going down the wrong path, let's do some print statements. So we have a little print statement for if they're overlapping. So we're going to add a system here for update, and that's going to be where we're registering this function call. So now every update frame, basically as often as the engine wants to give us, it'll try and check this. Let's see what we get. Does it explode? Oh, look at that. So we're getting a few things happening here. So it's pretty clear that this isn't actually checking for if we're already colliding, which is of course what we need to do next. It's also working between every 2 types of entities, which based on the way the game is designed is kind of what we want to do. There's some of those events that we're going to ignore, but for the most part, adventurers collide with treasure and goblins. Goblins collide with treasure and obviously adventurers. The only thing on this screen that only the adventurer interacts with is the exit. Pretty solid, pretty solid. Let's do the rest of this. So we need to check if the thing we're colliding with exists in our vector. Basically, if we are overlapping and we don't already have that entity inside of our list of things that we're colliding with, we're just going to chuck it in there. Same thing with collider 2 to collider 1. And then we're also going to want to basically do the same logic but in reverse down here. So these are the indexes inside of our colliding with vector where the entity we're colliding with is the other one we just collided with. This is returning an option, so it's either going to be some or none. If it's none, then we didn't find one, basically. So now we'll go and do something similar to here where we're just checking to make sure we found something. And if we did find something, it exists, so we can remove it. We're actually maintaining our colliding with lists. So when things are on top of each other, they are in the list, and when they're not on top of each other, they're not in the list. We want to fire off those events, but we only want to do it when something either enters one of those lists or exits one of those lists. So how we're going to do that is a simple Boolean tracker for whether or not these things happened. Now, it's a little bit wonky that we have to check this twice. Theoretically, there could be a way to design this where we can say for certainty that there's only one source of truth here, but as of currently, both colliders kind of have duplicate data. It's not a huge deal, but it's something that if we had more time, maybe we could design a better solution to this. So let's just do our print line statements directly here. Passing in collider1 name and collider2 name. So that'll print out the line only when there's a new collision being added. And we're gonna do very similar logic here. All right, let's see what we get. It's actually triggering when they're colliding and only when they're starting to collide or stopping collision. And that's exactly the behavior we want, because down the line we're going to be using these events and we want it to be only triggering the first collision. We don't want a whole bunch of, like say you get a point when you're colliding with a treasure, you don't want to get 30 points because you were colliding it with it for 30 frames, which is why we're filtering this out here. We're having these prints actually happen, which means now it's time to use the events that we defined before. The way we do that in Bevy is we have to pull them in just like we do a query from the top here. We're bringing these in. These are event writers for these events. And really what we're going to do is just replace this print line with a call to send a new collision enter event, for instance. And down here, of course, we're going to send a collision exit event. Simple as that. With that, this system's actually kind of done, which means we can actually go over real quick how we're going to consume these events. In order to do that, we're going to add a couple of systems for basically debugging these collisions. Kind of basically doing the same thing we were doing printing before, but we're going to do them in a separate system to prove we can. So we're pulling in our event writer. Actually, it's not going to be an event writer. Whoopsie. Reader. We're reading an event, not writing it. So obviously, when we debug these collision enter events, we need an event reader for that type of an event, and we're going to actually iterate through it. So if there are multiple event reader events that happen in between each call to this function, then we'll have them all in this list. Here we want to print out both entity names. Unfortunately, what we have in here are references to entities rather than references to our collider. So in order to grab a reference to our collider from those entities, we actually need a query to get that information. And this is the second most useful use for query that I've uncovered so far, is converting entities into whatever you need from the entity. So we could very easily be passing collider here, right? But we don't know what systems down the line are going to need from these entities. So instead, we're passing in the entities themselves and letting the systems decide what they want to pull out from them. In this case, we're just pulling out the collider itself. So we're using colliders.get, which a query.get takes in an entity. So we're getting entity 0 and we're getting entity 1, and we're basically mapping it to a collider. And coming back from this, it's a result that either gives an OK saying, hey, we found the collider, or it'll give a error saying, hey, something's amiss. Either there's no collider or something else went wrong. And we don't care if there's no collider, because we only care if these things exist. So we're completely disregarding that. We're going to write the same function for collision exit while we're at it. So now we have our two debug functions, which are basically doing the same thing our print lines are doing here, just separately. And now we can include this in here. So now we're passing those two in. So if we run this project, it should give us a very similar result that we got before. Look at that. Exactly what we were expecting. We're entering and exiting the things that we are entering and exiting. If you look here, focus on the adventure going in and out of the exit. It's going in and out. So this is actually, believe it or not, more or less all we need to do for a collision system. Later down the line, we're going to be obviously using this collision system to detect collisions between things. Probably the next thing we'll do is have the adventure murderize the goblinoid when they collide, and that'll be fun. One thing I want to do real quick to clean this up, just because we can, is I actually want to pass in a flag to our collision plugin as to whether or not we want to use debug messages. We're going to add a bool here. We actually were going to do a explicit named so that it's easier to tell what the heck that bool even means. We're going to remove these, and what we're going to do is if self debug. So this means if we're in debug mode, or if we've passed in the debug flag, then we can do add systems to update, and that's where we pass in the debug collision enter and debug collision exit. So, see it's complaining over here. We just need to tack in, whoops. We also need to make sure this is a public. There we go. So now we're passing in debug true. So if we run it like this, we'll get the same messages that we were getting before. There we are. Look at that. And if we pass in false, we should get no messages. Yay! All we have is our hydrators that we haven't built yet. I'm going to leave debug on. because we might as well have as much information about what's happening in our game as possible while it's under development. All right, so that basically wraps up what we were doing today. Next time we're going to actually consume these events for murderizing the goblinoid. We'll also do a little bit of basic, I hesitate to call it animation, visual and audio feedback for the said murder. That wraps it up. Thanks for watching. Peace. I like Java. I mean, it's kind of always a pain to work with because almost all the apps you run into with it are like ancient. So they're all using like Java 11 or something, at least in my experience. I mean, they were teaching OOP with Java when I was in school too. And the way Rust works with options, so Rust doesn't throw exceptions like Java does. It'll either panic and completely shut down if something is completely wrong, which is kind of like an exception except you can't catch it. Or it'll return either an option or a result. The option enum is basically a wrapper with context around the thing that's inside of it. So what we wanted was the position of whatever's in that vector. What we got back is, well, this could be something with a position inside that vector, or it could be nothing.